Okay.
So introduce yourself and I'll give you a 5-minute warning again.
Thank you. Okay, yeah, sorry that I'm back to back. So enhancing, that's the next paper I'll be presenting is enhancing software runtime with reinforcement learning driven mutation operator selection and genetic improvement. This is a paper by Damien Bose, myself, and Justyna Petke. So background on search-based runtime improvement of software. We select a mutation operator with a fixed probability. So for example, on the slide with 3 mutations, you'd have a third probability. Important to note that there's no limit on the number of mutation operators. It's just the idea it would be uniform. So if you have 5, it'll be a fifth each. You take the mutation operator with that specific probability, and once selected, you apply it to the program to transform it and create a variant. This variant is then evaluated for fitness to check its viability, and that's normally based on the number of tests that it passes, and whether or not it improves the runtime of the program. What we propose is reinforcement learning aided mutation operator selection. So just like before, at the start, we select an operator with a uniform selection, we apply it to the program to create a variant, we check its fitness according to the predefined fitness function, and based on what the fitness value of the variant that was created by that mutation, we assign a credit to the mutation. So a mutation that was applied to create a program, and if the program performed well, a higher credit would be assigned to the mutation that created it. And what we do is, based on this credit, we alter the probabilities of the mutations. So a mutation that generated a successful variant would be assigned credit and its probability would likely go up, and it has a likelihood of getting selected again. And we repeat this process, mutations are selected according to the new probability, we create new variants, we check their fitness, we assign the credit, probabilities switch again, and that's how we keep going with the search, constantly tuning the probabilities of the different mutation operators. Maybe at this point I can ask if that's clear, the idea of tuning probabilities. Amazing. Okay, so operator selection algorithms, there's so many, but we only experiment with 4 in this paper. The first 3 are probability matching, upper confidence bound, and epsilon greedy. And Emmerich smiling because we did this work together. That's what's cited at the bottom of the slide. We attempted to do this for automated program repair. And now with this paper, we do it for runtime. So these were the algorithms that we used in this paper. So we tried them again for runtime. And the reason they were chosen in that previous paper is because we found that they were heavily used in the literature for numerical optimization problems. With this paper, we use those as well, but we also add policy gradient because we see potential in possibly applying this for deep learning in the future. Okay, getting into methodology. Just like with the last talk, I'll only talk about the interesting stuff and the full details are in the paper. The tool that we used was Magpie, and the benchmark that we used was Minisat, which comes with 1,000 test instances, which we split into a training set and a validation set. 20 tests were used for training, and what I mean by that is that was used for fitness evaluation during search. And then 980 were used for checking the true runtime improvement after the fact. And the reason we did this split is based on past work. I think it actually was by you, Emmerich, where you say that 20 is a good enough number of tests used during search, if I'm not mistaken. And then 2 search strategies, neighborhood search and hill climbing. We did 5 repetitions in order to more accurately report on results, and we set a limited time budget, the same for all the runs. And we look at 2 different metrics. The best runtime improvement found, so that's the ratio of the new runtime to the original runtime, and also the percentage of unique variants evaluated that are successful. The main thing that we investigate in this paper is which operation selection strategy leads to the best efficacy and efficiency of search for both the neighborhood search and the hill climbing. Looking at the efficacy of the neighborhood search first, if we look on the left-hand side of the slide, it presents the ratio of runtime of best improvement to the original runtime. The y-axis presents the percentage of that, and then we have the different algorithms. We can see that the improvement was pretty much the same for all the operator selection strategies, and that's because probably with the time budget that we had, it was too large for the local neighborhood size of the mini-stat benchmark. So it kind of it all overfitted to that very quickly. And then on the right-hand side, we present the percentage of unique variants evaluated that were successful. So we can see that the uniform selector and epsilon gradient performed the worst. And then policy gradient is marginally better, but UCB had by far the highest percentage of unique variants with around 34%. I think what's more interesting is this, to kind of get a sense of what is going on behind the scenes. So I'll be presenting the run statistics for each of the operator selection strategies, starting with the uniform selector. And that's the one that selects always with the same probability. So obviously none of this actually affects the search. With the uniform selector, we're always selecting with equal probabilities. But we collected these statistics and plot them on the slide just to kind of get a sense of how it normally performs in terms of what the rewards look like and how the operators are getting selected. And what we see is very expected results. Yes, Bill?
You'd have to be. But it's very impressive the number of different operators you've got. When I first started, I was thinking, yeah, there's probably 3 or 4.
Yeah.
And you've got, what, 2 dozen?
Yeah.
So, as I say, maybe repeat just for people who are online.
So regarding the mutation, the question was maybe to highlight that the number of mutation operators that were used. We kind of went a lot with a lot of them, most of the ones that are implemented within Magpie, just to kind of be able to see the learning more clearly and not be, with 3 operators that are not converging as much, maybe. So yeah, you will see quite a lot. The break deletion and the return deletion and the expression statement deletion are the best performing. It seems in terms of the rewards, and this is pretty consistent across the board. They kind of switch around, but these are the top 3. And not very surprisingly, we see deletion in the name. Again, this was talked about in the keynote this morning. This is a very common occurrence with GI, especially for runtime. Deletion tends to perform pretty well because you can delete things like assertions and then have a higher, a more optimized version of the program very easily without affecting the functionality. Okay, so what we see basically around the 400 mark on time, I think that's milliseconds, the rewards kind of start to stabilize more. And on the right-hand side, we plot a number of times that each operator was selected over the course of the search. And we can see that the operators were pretty much selected the same amount. It's kind of a linear distribution for all of them, which is, again, not surprising because they have equal probabilities of being selected. Now, if we look at epsilon greedy, Emmerich laughing because this is a pretty funny graph on the right-hand side. We can see that the break deletion is getting chosen over and over and over again. And the average reward on the left-hand side shows it to have the highest reward. So that checks out, right? Because with the epsilon greedy algorithm, the best operator gets chosen 80% of the time. And then the other 20% of the time, we choose uniformly between all the other operators. So at that point, you kind of don't have a chance. You're greedily choosing the best operator over and over and over again. So if that operator continues to give you good rewards, it's going to continue to be chosen. And that's why on the right-hand side, we can see that the break deletion is, has that linear distribution. It's always getting chosen. And then the other operators are just kind of not doing that because, there's so many, and it's a 20% chance of them being selected uniformly at random. So you can see how that would make their probability of selection very low. The UCB now performs a little bit better. Yes? Here?
Yeah, I think one thing that might you playing the graph on the right, is because it's a deletion, so there might be very few of them. You can only delete something once. Because your graph is on the time of side of it, it might be that all the variants with deletion have been cached by MagPie. So that's why it grows that quickly in terms of time, because they are instantaneous to evaluate. It just put them, take them from the cache.
That's 1,000% right. And you will see that very clearly in graphs down the line. You will see that that's the issue with epsilon greedy. It kind of is always the outlier in our graphs. I don't know if the microphone is too loud. Okay. You will see that it's kind of the outlier in future graphs for that exact reason, and I will talk about it. So you bring up a good point. Yeah, for the people online, maybe I won't repeat, you will hear the same thing later on. Okay, so next for UCB, we can see that we have a better graph on the right-hand side. It makes more sense. We're not choosing the same thing over and over again. And that's because UCB balances exploration with exploitation much better than the epsilon greedy algorithm. So it has an internal ranking that doesn't only take into account the average reward per operator, but also the number of times that it was selected to be explored. And it tries to balance these two things within the formula of how it calculates what's getting chosen. So that's why we can see that while break deletion has the highest average reward, it is not always getting selected. And we have some if deletion and some return deletion also getting chosen. Now, probability matching, I think looks much better. And that's because it has another bound, and that's the probability minimum variable. So you can set a minimum probability for each operator to be selected. So, and that has to be strictly larger than 0. You can play around with this value. I think we went with the default in this paper, but all the operators have to be selected with a probability that's greatly greater than 0. And that means that even if they're performing very, very badly, I think the worst one is switch insertion, it's still getting selected. We can see that there's no flat green line at the bottom. And so it gives a chance to the worst performing operators in hopes of maybe being better down the line. And that's why we see the count kind of be a little bit more fair to the other operators. And then finally, we have the policy gradient. This plots the preference over time instead of the average reward. We can see that these graphs are not very interesting because on the right-hand side, it looks very similar to this, which is the uniform selector, meaning that not a lot of learning is happening. And we think that's because we set the learning rate way too low. And that is something that maybe can be explored in the future. I think all these like policy-based algorithms can be their own paper, and playing around with the learning rate would be essential in a paper like that. But here it's with a low learning rate, we're kind of very zoomed in on what the search would be, and it's very stuck on that uniform selection. Yes, Bill?
So there is a call for a journal extension. So
yeah.
Special of the ICSE journal.
Yes. Possibly to look into. Bill was saying that maybe we can explore this in the ICSE journal, which is can submit extensions of this workshop. All right, getting into the efficiency of the neighborhood search. Here we plot the number of iterations till the best patch is found. And we can see that for most of the algorithms, they pretty much overlap. But the epsilon greedy is definitely the outlier. And this touches on the point that Emeric brought up earlier, which is the fact that MagPie caches the fitness of variants that it's seen before. And with epsilon greedy, since it's choosing the same operator over and over and over again, in this case, it was a break deletion. There's probably not a lot of breaks to delete within Minisat. So at a certain point, you know, where you're just using the cached fitness and we're able to explore a lot more variants in a shorter time budget. And that's why we see the number of iterations be much higher. Okay, quickly going over the results of hill climbing. First, the efficacy on the left-hand side. Again, we're presenting the ratio of runtime best improvement to the initial runtime. And we can see that for all the learning-based operator selection strategies, they perform much better than the uniform selector. And then on the right-hand side, when we show the percentage of unique variants evaluated that are successful, the UCB performs the best, with 44% of the unique variants being successful variants. So that's actually very impressive. And then finally, looking at the efficiency of hill climbing, this was also kind of, it's probably hinting that the time budget that we should have given it for hill climbing should have been longer, because we can see that the median of finding the best patch found is very close to the 100% of the time budget. So there's a question here of perhaps if we doubled that time budget, maybe we could have found much better variance in that time. And then a few things to discuss before I wrap up. Much more comprehensive discussion in the paper, but one of the things is that the results for hill climbing were pretty similar to neighborhood search, with the break deletion, return deletion having the highest average reward. Again, makes sense, very typical for GI for deletion to be better performing. The best edit took 27.24% of the original runtime to evaluate the 980 test instances in the validation split. I want to say that with all of the variants that we have, we relied on test suites. So if it was test suite passing, we considered that a test passing patch. It wasn't manually analyzed to check if it's actually a correct patch that preserves the functionality and is actually improving the functionality to better the runtime. So this is possibly something to look into of a qualitative analysis of the patches. And then all the operator selectors heavily, I think I already talked about this, rely on deletion. I want to just mention that we only had the Minisat benchmark in this paper. We would like to maybe look into more benchmarks in the future because the generalizability based off one benchmark is not the most robust. And finally, hyperparameter tuning. So I talked about this briefly. Policy gradient has the learning rate that can be played around with, which I think will dramatically change the results because it was very clear from the graphs that it was too low. The minimum probability in the probability matching algorithm could also be played around with to explore more or less, and so on. That's it from me. Thank you so much for listening. Just checking if there's anything. Oh. That's not.
Are there questions online?
Why does anyone have? Oh, Q&A. Okay. Any questions in the room?
Are there questions in the room? So Amrik has already had. Did your last question? I will remember that. Your presentation is next. Amrik. So maybe use the microphone. Front of the mic.
So I have one question that might be slightly more technical from the list, because I know my work.
Yes, and the previous work, so you're probably the best person to ask questions.
From the list of mutations that I saw, deletion, you understand? Replacement, if you didn't change how it works natively in MagPy, it checks, it replaces only by the same type of node in the IST. So if you have, for example, break replacement, that would replace the break node by another break node, or not another type of statement. So you wouldn't be able to replace a return by an if, for example, or an if by return. So did you change that in your experiments?
No. The mutations were used exactly as is in MagPy. The only bit we played around with was the probabilities of selection. So yeah, possibly, because again, also, we kind of took the mutations here as is. I wonder if the results would change based on the number that we have. Maybe this is kind of making the learning too noisy. Maybe there's not maybe there should be more operators. You can play around with the number and with the types, and I'm sure they would somewhat affect the results. That's why I want to highlight that take generalizability here with a bit of caution, because it needs to be on more benchmarks and more variation with the mutation operators that we're using, right? In terms of number and in terms of what they're doing.
So yeah, for example, you do have a break placement in the list.
Mhm.
On break is something which has no argument, so every break is virtually the same. So every time you choose that, MagPie should detect that it's the exact same as the previous one, and it will be cached. So anytime you
Yeah.
add that to the list, it should be automatically cached. It will never evaluate it.
Okay. Okay.
So
And that's the whole that.
So this one will never have an impact because it will never reevaluate because it's the exact same of the
Yeah.
client.
For the people online, I'm sure, okay, with the mic, I'm sure they heard it. But that's a good point. That's something maybe that should not be a part of this list.
That could be easy for replacement. You just need to pick an ingredient that can be any type of
Yeah.
statement,
Yeah.
and then you get the statement to statement from
Yeah. I can definitely check with Damien, who ran these experiments, if he played around with changing the ingredient. But what I think is they were used as is and they were not changed, is probably what I would say likely happened.
Write an if statement by another if statement,
Mhm.
an if statement by a result.
Yeah. So it looks at the node type when it does that.
The difference is to rename every type of node to just statement, so everything is the same. By anything by anything.
Yeah.
But still a statement, so that the IST.
The default behavior of MagPie is using the same node type in the replacement.
So the default is to take all the statement types that SourceML generates and renaming all of them to just statement. So that you have only one type of statement, which is statement. And you replace a statement by another.
I see. So when you go into this more fine-grained kind of analysis, you risk kind of just getting stuck on changing the same node with the same node.
So I did ask if you had an example of things that I found.
I do, and they are in our repo, and they are on my extra slides I don't think they're in this uploaded version that's on this machine. But maybe we can talk about it in the discussion.
Okay, so I'm somewhat confused by this thing about break. If you remove a break, then presumably in a case statement, you go into the next. So,
or in a while loop, you could be infinite, or you can.
So why is deleting a break going to reduce runtime?
So because you have an IST, you can, for example, have in your function something that say if that happens, then return prematurely, and do not do that the next of the function, which might be expensive. And you remove the break, you do the expensive stuff all the time, and it might be beneficial to do the expensive stuff all the time. You just change the semantic of your function. You're removing an early return, for example, and it does something else, and that something else is more beneficial.
Yeah, for example, like it could be, calling a different function versus doing something expensive and then just returning or exiting. And then that way you're terminating a lot more quickly in the long run.
It's been a long time since I've done some C, but if breaks are used in switch, it might also be used to just do the next element in the switch. So that might be equivalent of changing another value, something else, somewhere in the program, because instead of doing option 1, 2, 3, we'll only do 1 and 3, because every time you go to switch number 2, you will end up doing switch number 3 instead. That will also happen, because it will fall through every case in the switch.
So is this an artifact of MagPie? or would you expect this sort of thing to happen in other programs?
I think it's just a magic serendipity of GI in general, when you evolve things, when you don't know semantically what it will do, it's just an happy happenstance of evolution. You will changing the IST in some way, and it will do something. So
we can also point out like return deletion is next, right? And you could argue that break deletion and return deletion are probably having the most impactful change to the semantics of the program. So with an evolutionary process, where you have so many variants that might converge to a very short program. Whereas replacing, like a declaration or one if statement might not have as big of an impact on the behavior of the program with the test.
Okay. So we're saying that these things break code. Sometimes they may break it in beneficial ways.
So the question is also,
they're not neutral operations normally.
yeah, but that's where I think manual analysis is beneficial here, right? Because you might be deleting stuff, completely changing the behavior of the program, having a much faster program, and it's passing your tests. But is your test catching all the paths of the AST that it should, it should run or not? So your tests have to be really good, and I think a step of manual analysis would have helped kind of give us a more concrete conclusion here.
Okay, just a quick reminder, there are cookies to ask questions. Doesn't have to be a great question. Grab a cookie anyway. So I think we have time for another question, which is here we're using Magpie, but you previously used Jin.
Yeah.
Have you got any words of wisdom about which one you prefer and why? Ignoring parts of the audience.
I don't know if I'm gonna fall into this trap with the audience of this workshop. We have Sandy and Justyna maintaining Jin, and then America maintaining Magpie. I would say Jin doesn't have currently a fault localizer in it. I think it depends on what you're running. It depends on what you're running. With Jin, since we have the previous paper that is already having the LLM implementation in it, it was very easy to implement the code completion stuff into Jin because the basis for that implementation was already there. For Magpie, we would have had to implement it from scratch. Whereas for this paper, since Magpie has the fault localizer, it kind of made more sense to do this instead of having Jin and relying on more basic search strategies. Just to say that. I don't know if that's, it depends what you're running.